At 3:40 a.m., someone logged into one of your company systems from a country where no employee lives. The password was correct. The VPN checked passed. No alert fired because no one ever wrote a rule for this particular thing has never happened before. That's a core problem with rule-based security. Rules catch the attacks you have already imagined. And here's what makes it harder. You have millions of login events and exactly zero of them labeled. This was an attack. You can't train a classifier on labels you don't have. This video kicks off a new series. Over 3 episodes, we are building a production grade behavioral anomaly detection system end to end. Today, the detector itself, from raw logs to a scoring API. By the end, you'll have a working system you can run locally and an evaluation that tells you honestly how good it is. Let's build it. Here's the full system across the series. Today, raw auth logs in, features, and unsupervised detector, a scoring gate, and a small API at the end. Episodes 2 and 3 make it smarter and keep it alive. More on that later. While real auth logs can't leave any company's walls, the patterns in them are universal. So the repo ships a generator that produces realistic login events. Users with home countries, work hours, regular devices, and this matters. It injects 3 known attack patterns: impossible travel, a new device at an unusual hour, and a credential stuffing burst. The labels go to a separate file the detector never sees. They exist for one purpose, so that at the end, we can score ourselves honestly instead of eyeballing the output. Let me show you the raw logs those were generated. So here you can see we have event ID, user ID, TS, device ID, country, latitude and longitude of the user, and success. Before we write any code, let's get precise about what we are hunting, because anomaly is one of those words everyone uses and almost nobody defines. The classic definition comes from the statistician Douglas Hawkins. An anomaly is an observation that deviates so much from the others that you suspect it was generated by a different mechanism. The last part is the whole game. A user login in at a weird hour is a deviation. An attacker using stolen credentials is a different mechanism. Our job is to separate those. And that's also why anomaly and outlier aren't the same thing. Every anomaly is an outlier, but plenty of outliers are just rare legitimate behavior. Hold that thought, it becomes a real problem in episode 2. Now, anomalies comes in 3 flavors, and here's what I love about our 3 injected attacks. Each one is a different flavor. Point anomaly, a single event that's weird on its own, no context needed. Our impossible travel attack, a login from Singapore 40 minutes after a login from Frankfurt. You would need a 12,000 kilometer per hour commute. One data point, obviously wrong. Contextual anomaly, an event that's perfectly normal in general, but weird in this context. A new device at an odd hour, a 2 a.m. login, is normal for an on-call engineer, and a new laptop is normal after an IT refresh. Both together for an accountant who is logged in from one desktop 9 to 5 for 3 years. That's one suspicious in context, which is exactly why context has to live in our features. Collective anomaly, events that are individually innocent, but from a pattern that isn't. Our credential stuffing burst. Each login attempt looks completely ordinary on its own. 500 of them across different accounts in 10 minutes is an attack. No single event rule can never catch this. You only see it in aggregate features. One detector, three different shapes of wrong. That's the bar. So, how do we catch all three without a single labeled example? Isolation forest. And the idea is almost embarrassingly simple. Most algorithms try to model what normal looks like and flag whatever doesn't fit. Isolation forest flips it. Don't model normal at all. Just try to isolate points and notice that anomalies are easy to isolate. Here's the mechanics. Build a tree, pick a random feature, pick a random split value between that feature's min and max. Divide the data into two. Recurse, keep going until every point sits alone in its own partition. Now ask, how many cuts did it take to isolate each point? A normal point sits in a dense crowd. Separating it from neighbors takes many cuts. An anomaly sits far out in feature space, often two or three random cuts, and it's alone. Path length is the signal. Do this with 200 random trees and average the path lengths, and you get a remarkably stable anomaly score. Short average path, anomalous. Long, normal. Why this algorithm work for our problem? Three reasons. It needs no labels. It never asks what an attack look like. It makes no distance or distribution assumptions. Our features will live on widely different scales. Kilometer per hour next to a 0, 1 flag. And isolation forest doesn't care. And it's linear time. It scales to login volumes real companies actually have. One honest limitation plus one trap before we quote. The limitation, the forest only sees the dimensions we feed it. Random cuts in feature space can't find an anomaly your features don't express. Feature engineering is doing half the work. That's next. The trap, the contamination parameter. It sounds statistical, but it's really you declaring what fraction of events you believe are anomalous. And it directly sets your alert rate. A 1% on 10,000 daily logins. You have just promised your security team 100 alerts a day. They will mute you by Friday. Remember that number. It comes back in the demo. Now, let's code our features. We have three features. First one is geo-velocity kilometer per hour. We want to calculate the speed required to travel between two consecutive locations. Device novelty. If this device has never been seen for this user, we'll try to create that feature. Next comes our R deviation. This is something like circular distance from the user's median login hour. So the model never sees raw coordinates or timestamps. It sees behavior. How fast would this person have had to travel? Is this machine new? Is this a weird art for them? Feature engineering is where domain knowledge enters an unsupervised system. The model can only find anomalies in dimensions you give it. Devices before of timestamp and median login hour of timestamp methods. These are the history strictly before the current event. Using the full history would leak the future. The same trap shows up in every ML system, and it's invisible until your production numbers mysteriously underperform your tests. Next, let's build our detector. So basically what we did is we have contamination 0.202, not the default, chosen from the alert budget math, not from the data. Every scored event emits one JSON log line with the score and the features that produced it. When a 2 a.m. page asks, why did this alert fire? The answer is already in the log. That habit comes from the debugging ML series, and it's non-negotiable in everything this channel builds. Also train a boring, robust Z-score baseline on geo-velocity alone. If the fancy model can't beat one threshold on one feature, we deserve to know. Now let's try the evaluation. So the harness replays all 50K events through the detector, then only now opens the ground truth file. So impossible travel or geo-velocity makes it a screen, find anomaly, easiest flavor. Credential stuffing burst via aggregate features. So we have got these credential stuffing burst as well, which is an collective anomaly. New device had odd hour, which was partially caught. Some victims were users with irregular schedules, so odd hour barely moved for them. That miss isn't a bug, it's the global model's blind spot. A contextual anomaly needs per user context, and that's exactly what episode 2 fixes. So, our baseline comparison, the Z score catches impossible travel just fine, cheaper, simpler, but is blind to the multi feature pattern. The operational number alerts for 10K events. A detector that cries wolf gets ignored, and an ignored detector is worse than no detector. So let's show you the solving layer. So we have 20 lines of fast API, post a login event, get back the same decision ticket the gate produces, same logging path. I'm not building this on camera because serving done properly, registry, CI, rollback is its important episode later in this journey. But the system is end to end today. Login gets code. Let me show you the sample example request. What we have now, behavioral features that encode domain knowledge and isolation forests tuned to an alert budget instead of a default, a structured log for every decision, and an evaluation against known attacks instead of vibes. But you also saw the crack, the night shift worker. Our model has one definition of normal for everyone. And the moment someone legitimate works unusual hours, we either flag them every night or miss attacks hiding in their noise. Anomalous. Relative to whom? That's episode 2. One question: does your team evaluate models against known cases or eyeball the output? Yes or no in the comments. I read everyone. If you want real AI engineering content, production war stories, working code, no textbook theory, subscribe. New video every week. See you next week.